Well, welcome. In this video, we're going to be covering a brand new concept about the end behavior of sequences. And in this video, I'm going to be giving you a lot of information. So it's going to be really important that you get a lot of this down into your notes. That might mean that you have to pause the video. That might mean that you have to kind of go backwards and get it all. But you want to make sure that you get this concept, because this is an important concept that we're going to be talking about in this chapter. And it's all about, like I said, the end behavior of sequences, or another way to look at it is the limit of sequences. Now, all an end behavior is if you were to look at a graph, if you were to graph a sequence, I should say, and if you were to track it along the x-axis and look at it in terms of infinity as you continue to travel along the x-axis, if there's a value that graph, that those points start to approach, if they get really close to, that is what we call the end behavior. And so we're going to be looking at the end behavior as we follow that graph, as we look along the x-axis, as we follow it to infinity to see what that graph is doing. So let's look at some graphs. We're going to start by looking at a couple of graphs here. You want to make sure that you, as far as what you get in your notes, there's going to be, you can see one graph to my left here. There's another one that I'm hiding right now with my video. But once I remove this picture of myself, you'll see the two graphs. So it's going to be important that you get those two graphs in your notes. Below there's going to be some information to write down about those graphs. And like I said, I'm going to start out with a lot of information, but once you start to apply it, you're going to see that the information starts to make sense. So let's start by looking at these two graphs and then formulating some information and some things that we need to know about limits of sequences. Okay, so these are the two graphs that I was referring to. So again, in your notes, draw a graph of this first one and the second one. Now this first one, this is representing the sequence for this explicit formula, -2 times n. So to get these numbers, to get these values, they're again using that explicit formula where the first term would be where n is 1. -2 times 1 is -2. To get the next term, they've put 2 in for n. -2 times 2 would be -4. To find the third term, you put 3 in for n, and so on, and it would give you this sequence. And again, it would keep going on for infinity. This one over here has a special name for it, and this is really, really important. We're going to be talking about this sequence a lot in this lesson. This is called the harmonic sequence. And if you want to look in your book, it'll describe why it's called the harmonic sequence, but I'm not going to take the time right now to talk about that. But this is called the harmonic sequence. So just like before, this is an explicit formula. You put 1 in for n to get the first term. 1 divided by 1 is 1. Put 2 in for n to find the second term. 1 divided by 2 is 1/2. Put 3 in there for n, you get 1/3, and so on. Now, again, what I'm going to do is I'm going to scroll down here. So I want you to pause the video. And I want you to write down this information. Let me get all of it, see if I can get all of it here. So I want you to write down the information that we have here. Get this all in your notes. So pause the video, especially the parts that I've highlighted here. These are the important pieces. So pause the video so you can get all that written down first. And then hit play when you're ready to listen as I explain what each of these pieces represent or what these pieces mean. So again, pause the video now. Hit play when you're ready to go over this. Okay, so let's start with this first paragraph here. It talks about this first sequence. So as we look at that sequence, as my values for x, as my terms are increasing, my values for those terms continue to decrease. And they continue to decrease without approaching any particular value. So we say that it decreases without bound. The other graph, on the other hand, for our harmonic sequence, as my terms are increasing, my values of those terms continue to get closer and closer to our value here of 0. Now think about why that is. We have the equation 1 divided by n. Well, if you notice, we have a horizontal asymptote of 0 because we're never going to have a value. We can't divide by 0. So we're never going to have a value equaling 0 in our equation here. So there's never going to be an answer that we can get equal to 0. So that's significant. We're going to talk about that later. Now, these values in our sequence, again, are approaching this value of 0. So the way that we describe that is we say that 0 is the limit of c sub n, or it's the limit of that sequence as n approaches infinity. Now granted, I don't want to write that every single time, so we have this piece here that helps us
write this in a much shorter manner, saying that the limit for the sequence as n approaches infinity equals 0. So that's a much shorter way that we could write it. Now going back to this other sequence. That sequence doesn't have a limit because it continues to go, the values continue to get larger and larger negative numbers as our values for our term values increase. So the way we describe that is we say the limit for that does not exist. Now situations like that where there is no limit that exists, we say that they diverge or they are divergent, having nothing to do with the popular book. Now, on the other hand, if there is a limit, we call that limit L. If there is a limit, we say that it is convergent, or it converges to that value of whatever the limit is. So in your assignment, you'll be asked if situations are divergent or convergent. So they're divergent if there is no limit. They're convergent if there is a limit. And we'll learn more in a little bit how to find out what that limit would be. Now, a constant sequence, anytime we have a constant, like if I have a sequence of just 5, that means if I were to graph it out, I'd have my first term of 5, a second term of 5, a third term of 5, a fourth term of 5, and so on, where it'd be nothing but 5s. We would say then that it's convergent, and it converges to that value of 5. So if I have a sequence of -2, and that's my constant of just -2, we would say it converges to -2. Now you don't have to worry about writing this piece down. We've already talked about that a little bit in the previous part of our notes above there. But this is really important. Again, that harmonic sequence that we've referenced in that graph that was to the right, that harmonic sequence is 1 divided by 2. Well, we have this property now called the limit of our harmonic sequence property. Refers to the fact that the limit of that sequence is always going to be 0. And we're going to use that for more complicated sequences here in a little bit. So it's really important that we memorize and learn the fact that the limit as n approaches infinity for our sequence 1 divided by n, or for a harmonic sequence, is always going to be 0. Now all graphs of convergent sequences have horizontal asymptotes, and that's important because if you're ever not sure what the limit would be, you can always graph it out. And if it has a limit, it's going to have a horizontal asymptote. And whatever that horizontal asymptote would be is your limit. And we'll, again, talk more about how to find those limits here in a little bit. Now, in this next piece that I scroll down to, you do not have to copy down all of these properties of limits and constants. We're going to talk about some of them, but you're going to see that the way that they look is more complicated than the concept really has to be. So I don't want to overwhelm you and freak you out when you see some of these properties in a minute. We'll talk about one in particular to see how simple those properties really are. So here's those properties. Let's look at that one that I have starred there, and let's look at this graph over here on the left. So down here it's showing us that harmonic sequence that we've already talked about. And we can see that that harmonic sequence is approaching 0. Well, what if I had the sequence 1 divided by n plus 2? Well, using our graph translation theorem that we've talked about in the past, we would say that the graph is going to be shifted up 2 units. Well, what happens then is that limit that we had of being at 0, or the horizontal asymptote at 0, is going to be shifted up 2 units. So the limit for this particular sequence is going to be at 2. And you can see that the graph approaches and gets closer and closer to 2. And the reason why that we could describe that would be using this property, our second property here. Because what this property is telling us is that if we have a limit as n approaches infinity for a particular sequence plus a constant, we can break that up into 2 pieces to find the limit of that particular sequence plus whatever our constant is. So for example, with this one, we have our sequence 1 divided by n. We know that limit is 0. Our constant here is 2. And remember, our limit for any constant is whatever the constant is. So in this case, our limit would be 2. And this piece here, our limit would be 0. Add those together, we get a limit of 2. So we wouldn't have to see our graph to be able to get that. Or, for example, if we look at this quiz yourself, the QY down here, this is from our textbook. If I have 16 plus 1 over n, again, here we see that this piece here has a limit of 0, and our constant is 16. So 0 plus 16 gives me 16. So the limit of that sequence would be equal to 16. So again, what's highlighted here, by knowing that limit of the harmonic sequence is always 0, we can apply those properties to find the limit of a sequence with a more complicated formula. For example, take a minute now and write down these two sequences, 5n plus 1 over n and 3n plus 2 over n. So take a minute and write those down in your notes, so that way you'll be ready to follow along here in a second. Okay, let's actually start with the one on the right, the 3n plus 2 divided by n. We're going to start by, because this is one giant fraction, we can, since we're dividing by n, we can break this up into two smaller fractions, meaning that we take 3n divided by n and take the 2 divided by n. Now 3n over n, that simplifies to just be 3. Now remember, this does not look exactly like the harmonic sequence. The harmonic sequence is 1 divided by n. This is 2 divided by n. But remember, the reason why we had a limit of 0 was because since we can't divide by 0 with 1 divided by n, that means that you'll never have an answer of equal to 0, so you'll have an asymptote here of 0. The same thing is true for 2 divided by n. So it doesn't matter what the numerator is if the denominator is just a plain old n, or even n squared or n cubed for that matter, your answer is going to be 0. That limit is going to be 0. The limit of just 3 then is just 3. So my answer here, the limit as n approaches infinity for this sequence, for q sub n, is going to be 3. That would be your answer. So I want you guys to try this one now on your own. See if you can't simplify this one just like we did in this example, and use the information that we just did to see if you can't figure out what the limit for this sequence would be. So why don't you pause the video and hit play when you're ready to check your answer. Okay, let's see how you did here. So you should have gotten 5 as your answer. And again, you want to be in the habit of writing it as a limit. So this is one way you can write it. You can always replace the sequence name with 5n plus 1 divided by n as well. So sometimes you'll see that. But otherwise, this will suffice 2 as your answer. Now, if you didn't get 5, the reason why is you break this fraction up into two pieces to get 5n over n plus 1 over n. 5 over n simplifies to just be 5 plus 1 over n. The limit of 1 over n, that's your harmonic sequence again, so that's 0. The limit of 5 is just 5. Add those together, 5 plus 0, we get 5 as your limit. Now, we're going to look at some more properties here in a second. And again, these properties, you don't have to worry about writing these all down. These are more of what I would call common sense properties. If you want to write them down in your notes, you can. You'll want to pause the video if you're going to do that. Some of the words here got cut off, as you can see by that table. I didn't recognize that when I put that together. But again, I don't want to overwhelm you by these because they look more complicated than they have to be. I'll explain them as we go through them. So here they all are. So again, there's a lot of information here. Let's start out with the first one. It's called the limit of a sum property. All that's saying is if we're trying to find the limit of two sequences being added together, well, you can just take them and break them apart to find the limit of the first sequence, find the limit of the second sequence, add those two limits together. Kind of like what we just did in the previous examples. The limit of a difference property says that if we're trying to find the limit of two sequences that are being subtracted from each other, again, we could break those up into two pieces. Take the limit of the first one, subtract from that the limit of the second one. We have the limit of a product property, which we're going to do an example of one of those here in a minute. That just says that if we're trying to find the limit of two sequences being multiplied together, we can find the limit of the first one, find the limit of the second one, multiply those together. Well, guess what? We're also going to have one dealing with division. Go figure. Where we take the limit, if we're having the limit of a particular sequence divided by the limit of another sequence, just take the limit of the first one divided by the limit of the second one. So let's look at this one here. So sometimes in your homework assignment, this is all you'll see. They'll ask us to use the properties to find the limit as n approaches infinity for the two sequences multiplied together. Well, from the properties we just talked about, what we'd want to do is we want to find the limit of the first sequence, find the limit of the second sequence, and then multiply them together. So let's do that. So why don't you guys actually pause the video, and I want you guys to find the limits of these two sequences on your own. So pause the video and do that, and then once you get done, hit play and check your answer for part A, and we can talk about part B together. Okay, so let's see how you did here. I did the work up above the sequences there, the explicit formulas for those sequences. So for this first one, we end up breaking it apart, and you can see then that you get a limit of 7. For the second one, break it apart, and you can see then that we get a limit of 4. So to answer this question as far as what would the limit be for sequence P times sequence Q, you just multiply those two limits together. So 7 times 4 would give us a limit of 28. Now, your book doesn't always do a great job of explaining how to find some of these limits. So for example, sometimes they'll ask to find limits of expressions like the ones that I have here. Well, there's a little trick that we can use, so let me, even though it's summarized there, let me just illustrate it first and then we'll talk about it. So for example, this first one would be negative 8/12, which reduces to negative 2/3 to be your limit. The second one would be 4/12, which reduces to 1/3 to be your limit. And the last one here would be 7/7, which reduces to just be 1 to be your limit. Now notice a pattern here. Notice where I'm getting these numbers from. Well, what I'm doing is in the summary box, if the degree in the numerator matches the degree in the denominator, divide the leading coefficients to find the limit. What does that mean? Well, let's look at the first one. The degree of the first one, the numerator and denominator both have a degree of 1. So the degree matches in the numerator and the denominator. So then we take the leading coefficients, the negative 8 and the 12, and divide those. Well, negative 8/12 reduces to negative 2/3. Let's look at the next one. The degree for that one in the numerator is 2, and the denominator is also 2, so the degrees match. So then we would take the leading coefficients, the 4 divided by 12, divide those, and we get 4/12, which reduces to 1/3. And lastly, the degree here would be 3 in the numerator and 3 in the denominator, so again, the degrees match. So then we're going to use the leading coefficients, the 7 and the 7. Divide those, you get 1. So if the degree in the numerator matches the degree in the denominator, divide the leading coefficients to get the limit. Now, what if they don't match? Like what if we have situations like we have here, where we have a degree of 2 and a degree of 3, or 3 and 2? Well, if the degree in the numerator is smaller, so if the degree in the numerator is smaller than what we have in the denominator, the limit is always just 0. So again, doesn't matter what the leading coefficients are. If the degree is smaller in the numerator than what we have in the denominator, your answer is always 0. If the degree is bigger in the numerator than what we have in the denominator, your answer is going to be that there's no limit that exists. So that would be your answer. So again, this little trick that I just showed you applies to everything we've even talked about already today. So for example, with the two that we were just doing, here we have the degree would be 1. Here we have a degree of 1, so the degrees match. The leading coefficient in the numerator is 7. The leading coefficient in the denominator is 1. 7 divided by 1 is 7. Here we have a leading coefficient, a degree of 1 and another degree of 1, so they match. And 4 divided by 1 would just be 4. Let's even look at that harmonic sequence. 1 divided by n. Here in the numerator, 1 is the same as n to the 0 power. In the denominator, we have n to the first power. So the degree in the numerator is smaller than what we have in the denominator, so our answer is always 0. So again, those two tricks that I just showed you here at the bottom, at the end of our notes, that is not going to be described in our book. This is something that I'm sharing with you to make things a lot easier for you when you're trying to find these limits. So hopefully that's come together now for you, and this has made sense. And good luck now as you work on your assignment.